Well, hello, welcome back to College Physics 1. We're now into the second lecture of the thermodynamics section. And so we spent 5 lectures talking about mechanics. And so hopefully that's a little bit clearer. And we're seeing that as we build on each one of these topics, we use the material from previous lectures. And so now we're into thermodynamics. We covered momentum, impulse, and collisions last time. And now we're going to be getting into rotational motion and gravitation. And so this may be interesting for you. It gets into astronomy a little bit. And if that's something that you've ever thought about, you'll like this lecture. And I think we'll also get a chance to see some applications into various other areas, biology, kinetics, and what have you, with some of the other things that we'll talk about. So we're just showing an Earth Moon system with those 2 illustrations here with our cover here. And so, like I said, rotational motion and gravitation is what we're going to be focusing on. And as is the usual case, we'll start out with the reading questions, get into the main material of the lecture. We'll have various engagement questions throughout the material, then we'll have a summary. So for the reading question number 1, a rigid object is rotating with an angular speed of omega greater than 0. The angular velocity vector w and the angular acceleration vector are anti-parallel. The angular speed of the rigid object is, so you can think about that a little bit. And the answer is it's counterclockwise and decreasing. Next question is, the Earth remains in orbit around the sun rather than falling into the sun because, what do you guys think, if you have any thoughts on that? It says, although the Earth is constantly being pulled towards the sun, it is always moving with a velocity component perpendicular to the direction that it is being pulled. And so this is where you get into this angular dynamics with gravity, how you have a couple of forces acting on at one time. And so the velocity of the object, as well as the gravity coming from the sun, if we're thinking in terms of the Earth. A space station orbits the Earth with constant speed. What can be said about the space station's acceleration? So it's less than 9.8 meters per second. So that's the acceleration of gravity, because the space station is so high above the Earth's surface. And so if you might remember that 9.8 meters per second is the gravitational attraction at sea level. So the space station is something on the order of like 200 miles above the Earth. And so that's the reason why we're seeing it's going to definitely be less than that. So that's kind of the level of fidelity of what would be okay for us to be thinking at this level with this overview survey of these various aspects of physics. So for this one, select the best phrase that completes the following statement. The gravitational force of the Earth on an object is a function of the object's mass. And so the larger the mass of an object, the more that the gravitational force of the Earth will be felt. So if you have a car versus maybe a book, it's pretty obvious that the mass of the car is going to be much greater, and so there would be more gravitational force as a result. Which of the following forms of energy is the greatest for a system of a comet in orbit about the sun during the comet's closest approach to the sun? And so this is one of those areas of Kepler's equations that we could define. And so this term here is where the comet is closest approach to the sun. So the answer to this is the kinetic energy. So we'll see that as we go through the material today. And finally, which of the following trips would consume more fuel for a given spacecraft? And so this would be a trip from the Earth to the moon. And so there's a lot more gravitational pull on the Earth that you have to overcome to get to the moon. And so you can see that that would be much easier than going from the moon to the Earth. So that's something that you'll hopefully get a bit of understanding as we go through this material and perhaps think about it a little bit more. So let's get into the topic discussion. Once again, we're talking about rotational motion and how rotational motion and gravitation, how we characterize that kind of a system. So we experience rotational motion every day. The Earth's rotation creates the cycles of the day and the night. Rotating wheels make it easier to get around. Gears in a Swiss watch rotate. The concepts of angular velocity, angular acceleration, and centripetal acceleration are important to our understanding the motions of a car moving around a circular racetrack or clusters of galaxies orbiting a common center. In this topic, we will explore rotational motion for objects from bicycle wheels to orbiting planets. So maybe if dealing with astronomy isn't something that's familiar or of interest, thinking in terms of various forms of exercise or understanding the dynamics of how, say, like a bicycle work, we'll get a chance to see the angular elements of a bicycle. Okay, well, we'll get into some of the math as we develop this. And so when we studied linear motion, we needed to understand the concept of displacement delta x and velocity v and acceleration a. Each of these has an analog in rotational motion, the angular displacement delta theta, angular velocity omega, and angular acceleration alpha. And so this is what we're going to start to be playing out as we build this perspective. So first, let's look at some fundamental ideas. You know that the distance s around the circle is given by 2 pi r, where r is the radius of the circle. Dividing both sides by r results in the expression shown. So notice that this is a dimensionless quantity since s and r have dimensions of length. So the dimensions cancel out. And so that's the reason why that works out. So 2 pi corresponds to 360 degrees, pi to 100 degrees, and pi over 2 to 90 degrees. And this is going from radians to degrees, if you've ever heard of that term radians. Let's introduce a new unit of angular measurement, the radian. And so we're 180 degrees equals pi radians. And so that's something that's useful for you to be thinking about. So in the figure, for a circle of radius r, 1 radian is the angular subtended by an arc length equal to r. And so that's what we're trying to show there. So take a look at the circle, the angle theta subtended by an arc length s along a circle of radius r measured in radians counterclockwise from the positive x-axis is shown. The angle theta is an angular displacement from the positive x-axis, and s is the corresponding displacement along the circular arc, also measured from the positive x-axis. The angle shown in the figure illustrates the size of 1 radian, which is approximately 57 degrees. So converting from degrees to radians requires multiplying by the ratio of pi radians over 180. And so 45 degrees is pi over 4 radians. So generally, angular quantities in physics must be expressed in radians. Be sure to set your calculator to radians mode. So that's important, or else you're going to have to do that translation going from degrees to radians. So here we have 2 figures for the A, the point P on the rotating compact disk at T0, and for B, the disk rotating P moves through an arc length S. So the figure shows a top view of a rotating compact disk. So that may be something that you're familiar with, compact disks or CDs. This is an example of a rigid body where each part of the body is fixed in position relative to all the other parts of the body, where a rigid body rotates through a given angle. All parts of the body rotate through the same angle at the same time. Look at the figure on the left. Look at the figure on the bottom, I should say. For the compact disk, the angle of rotation is at the center of the disk. A point P on the disk is at a distance r from the origin and moves about O in a circle of radius r. Now we set up a fixed reference line and assume that at time equals 0, the point P is on the reference line. So after a time interval delta t, the point P is advanced to a new position as shown in the figure on the right. In this time interval, the line OP has moved through the angle theta with respect to the reference line. This angle theta is measured in radians and is called the angular position. It is analogous to the linear position variable x. Notice that the point P has moved in arc length S measured along the circumference of the circle. So here we have a figure as a point on the compact disk moves from A to B. The disk rotates through the angle delta theta equals theta F minus theta I. And in this figure, as a point on the rotating disk moves from A to B in time delta t, it starts at angle theta and ends at the angle, starts at angle theta I and ends at angle theta phi. The difference theta F minus theta I is called the angular displacement. An object's angular displacement delta theta is the difference between the final and the initial angle. So let's work a quick example. So if a point on the disk is at theta I equals 4 radians and rotates to an angle of theta F of 7 radians, angular displacement is delta phi equals 3 radians. We use angular variables to describe the rotating disk because each point on the disk undergoes the same angular displacement at any given time interval. So we can rewrite our equation for theta like this, where delta S is the displacement along the circular arc subtended by the angular displacement. Now we are ready to define an angular velocity. For very short intervals, the average angular velocity approaches the instantaneous angular velocity, just as in the linear case. The instantaneous angular velocity of a rotating rigid object is the limit of the average velocity as the time interval delta t approaches 0. We take omega to be positive where theta is increasing, that is counterclockwise motion, and negative when theta is decreasing, clockwise motion. Where the angular velocity is constant, the instantaneous angular velocity is equal to the average angular velocity. The instantaneous angular speed of an object is defined as the magnitude of the instantaneous angular velocity. Instantaneous angular speed or angular speed has no direction associated with it and carries no algebraic sign. So for example, if one object is rotating counterclockwise with an angular velocity of +5 radians per second, and another object is rotating counterclockwise with an angular velocity of -5 radians per second, both have an angular speed of 5 radians per second. So let's do a quick question here. And so a rigid body is rotating counterclockwise about a fixed axis. Each of the following pairs of quantities represents an initial angular position and a final angular position of the rigid body. Which of the sets can only occur if the rigid body rotates through more than 180 degrees? And the answer is 1 radians, 5 radians. And so for a rotation of more than 180 degrees, angular displacement must be larger than pi equals to 3.14 radians. The angular displacement and the three choices are for A, it's 6 minus 3 radians, which gives 3 radians. For B, it's 1 radians minus a -1 radian, which is 2 radians, and C, which is 5 minus 1 radians, this is 4 radians. So here's another question. Once again, a rigid body rotates counterclockwise about a fixed axis for exactly 1 second. Each of the following pairs of quantities represents an initial angular position and final angular velocity. Which choice represents the lowest angular speed? And the answer is -1 radian to 1 radian. And the reasoning behind this is because all angular displacements occurs at the same time interval, the displacement with the lowest values will be associated with the lowest average angular speed. Okay, well now let's look at a bicycle example, and perhaps you've been in this situation trying to adjust your bike. And so here we have an accelerating bicycle wheel rotating with a velocity, angular velocity of vi at time ti, and b an angular velocity of vf and at time tf. So the figure shows a bicycle turned upside down, so a repairing technician can work on the rear wheel. The bicycle pedals are turning so that at time ti, the wheel has an angular velocity omega I, the figure on the left, and at a later time t sub f with angular velocity omega f at the figure on the right. A changing angular velocity leads to the concept of an angular acceleration. So once again, we're talking about acceleration, which we've mentioned before, but now when it's in an angular domain. An object's average angular acceleration during the time interval delta t is a change in its angular velocity divided by delta t. Positive angular accelerations are in the counterclockwise direction and negative angular accelerations in the clockwise direction. So let's use our definitions to solve a problem. If the angular velocity goes from 15 radians per second to 9 radians per second in 3 seconds, the average angular acceleration during that time interval is -2 radians per second squared. So we see that spelled out in the equations there. So the negative side indicates that the angular acceleration is clockwise, although notice that the angular velocity is still positive, but slowing down is in the counterclockwise direction. So there is also an instantaneous version of angular acceleration. The instantaneous angular acceleration is the limit of the average angular acceleration over delta t as the time interval approaches 0. When a rigid object rotates about a fixed axis, every portion of the object has the same angular velocity and the same angular acceleration. So you might want to keep that in mind. So let's compare the defining equations for the average angular velocity with that of the average linear velocity. In these equations, omega takes the place of v and theta takes the place of x. So the equations differ only in the names of the variables. So you can just do this comparison in your mind between the linear motion and the rotational motion that we are covering now. Every linear quantity we have encountered so far has a corresponding, quote, twin in rotating motion, so we can write equations of rotational mechanics. The table shows both linear and angular versions that you can be mindful of. So here's another question. A rigid body is rotating counterclockwise about a fixed axis. Each of the following pairs of quantities represents an initial angular position and a final angular position of the rigid body. If the object starts from rest at the initial angular position, moves counterclockwise with constant angular acceleration, and arrives at the final angular position with the same angular speed in all 3 cases, for which choice is the angular acceleration the highest? And so the answer is the second case, -1 radian, 1 radian. And the reason is from alpha equals omega squared over 2 delta alpha, it is seen that the case with the smallest angular displacement involves the highest angular acceleration. In this figure, we're seeing a rotation of an object about an axis through O, the z-axis that is perpendicular to the plane of the figure. Note that point P on the object rotates in a circle of radius r centered at O. So let's take a look at an arbitrary shaped object rotating about the x-axis through point O. The z-axis is pointing out of the slide. Let's assume that the object rotates through the angle delta theta, and so point P moves through the arc length delta S in the interval delta t. We can write the relationship shown. So let's divide both sides with the equation by delta t, the time interval during which the rotation occurs. When delta t is very small, the angle delta theta is also small, and the ratio delta theta over delta t is close to the instantaneous angular velocity omega. On the other side of the equation, the ratio delta s over delta t approaches the instantaneous linear speed v for small values of delta t. This means that when delta t gets arbitrarily small, we get this relationship. So we're kind of seeing that we're bumping into calculus with these instantaneous values that we keep coming up to, but we're just, you can be thinking about that, although we're not really getting into calculus, but you're seeing these type of relationships that can be derived rigorously by using calculus. So have we just discussed in the figure, the point P traverses a distance delta S along a circular arc during the time interval delta t at a linear speed of v. The direction of P's velocity vector v is tangent to the circular path. The angular component of v is omega equals vt, which is called the tangential velocity of a particle moving in a circular path, written as shown. The tangential velocity of a point on a rotating object equals the distance of the point from the axis of rotation multiplied by the angular velocity. So this equation shows that the tangential velocity of a point on a rotating object increases as the point is moved outward from the center of rotation towards a rim, as expected. However, notice that every point on the rotating object has the same angular velocity. Tangential speed is the magnitude of the tangential velocity and is also called the linear speed. Keep in mind that this equation is valid only when omega is measured in radians per unit time. You might come across other measures of angular velocity, such as degrees per second and rotations per second, but these angle measurements need to be converted to radians. Let's now imagine that the rotating object changes its angular speed by delta omega in the time interval delta t. At the end of the interval, the speed of a point on the object, such as P, has changed by the amount delta v t, as we see in the equation. Let's divide both sides by delta t. On the left-hand side of the equation, note that the ratio delta vt over delta t tends to be tangential acceleration of that point. As the time interval delta t is taken to be arbitrarily small, delta omega over delta t approaches the instantaneous angular acceleration. So the tangential acceleration of a point on a rotating object equals the distance of that point from the axis of rotation multiplied by the angular acceleration. Again, radians measure must be used for the angular acceleration term in the equation. So let's do another question here. So Andrea and Chuck are riding on a merry-go-round. Andrea rides on a horse at the outer rim of the circle platform, twice as far from the center of the circular platform as Chuck. Who rides on the inner, Chuck, who rides on the inner horse when the merry-go-round is rotating at a constant angular speed. Andrea's angular speed is, the answer is the same as Chuck's. So we're talking about angular speed. So keep that in mind. All points in a rotating rigid body have the same angular speed is the rationale for that. Okay, so Andrea and Chuck are riding on the same merry-go-round in the same position. When the merry-go-round is rotating at a constant angular speed, Andrea's angular speed is twice of Chuck's. And so Andrea and Chuck have the same angular speed, but Andrea is moving in a circle with twice the radius of the circle followed by Chuck's. Thus, Vt equals R omega. It is seen that Andrea's tangential speed is twice of Chuck's. So here, if maybe you've either have one or your parents had one, had a CD player or a phonograph. You might still have a CD player of some sort. So before MP3s and streaming became the mediums of choice for recorded music, compact disc and phonographs were very popular. There are similarities and differences between the rotating motions of phonographs records and that of compact disc. Phonograph record rotates at a constant angular speed. Popular angular speeds were 33.5 revolutions per minute for long play, and were nicknamed LPs. 45 revs per minute were for singles, and 78 revs per minute were used for very early recordings. At the outer edge, the recording, the pickup needle called the stylus moved over the vinyl material at a faster tangential speed. When the needle is closer to the center of the recording, that means that the sound information is compressed into smaller lengths of track near the center of the recording than near the outer edges. CDs, on the other hand, are designed so that the disc moves under the laser pickup at a constant tangential speed. Because the pickup moves radially and it is following the tracks of information, the angular speed of the compact disc must vary according to the radial position of the laser. Because the tangential speed is fixed, the information density per track anywhere on the disc is the same. So we're seeing a slightly different approach for how they're recording information on both of those mediums. So let's look at these figures. So for A, the circular motion of a car moving with a constant speed. So you can think of a roundabout. And B, as the car moves along the circular path from A to B, the direction of its velocity vectors changes. So the car undergoes a centripetal acceleration. So the top figure shows a car moving in a circular path with a constant linear speed v. Even though the car moves at a constant speed, it still has an acceleration. To understand this, let's consider the defining equations for average acceleration. The numerator represents the differences between the velocity vectors vf and vi. These vectors may have the same magnitude corresponding to the same speed, but if they have different directions, their differences can't equal zero. The direction of the car's velocity as it moves in the circular path is continually changing, as you can see in the bottom figure. For circular motion at constant speed, the acceleration velocity always points towards the center of the circle. This type of acceleration is called centripetal or center-seeking acceleration. Its magnitude is given by this equation. So you have this one force that's trying to make it go towards the center. So in this figure, for an A, as the particle moves from A to B, the direction of the velocity vector changes from Vi to Vf. And B, this is the construction for determining the direction of the change in velocity delta V, which is toward the center of the circle. So let's derive this equation. So consider the figure. So on the top, an object is first at point A with a velocity Vi at time ti, and then at point B when velocity is Vf, and at time Tf we assume Vi and Vf differ only in direction. Their magnitudes are the same. To calculate the acceleration, let's begin with the average acceleration equation, where delta t is very small and delta s is very small, and delta where delta t is very small and delta s and delta theta are also very small. So in the figure, we see on the bottom v sub f is almost parallel to v sub I, and the vector delta v is approximately perpendicular to them, pointing towards the center of the circle. In the limiting case where delta t becomes vanishing small and delta v points exactly towards the center of the circle, and the average acceleration becomes the instantaneous acceleration. Notice that from the equation for average acceleration, A and delta v point in the same direction in this limit, so the instantaneous acceleration points to the center of the circle. The triangle in the figure, which has sides delta s and r, is similar to the one formed by the vectors in the figure. So the ratios of their sides are equal. Substituting, we get the expression shown. But delta S is the distance traveled along the arc of the circle in time delta t. And in the limiting case, when delta t becomes very small, delta S over delta t approaches the instantaneous value of the tangential speed, v, at the same time, the average acceleration approaches the instantaneous centripetal acceleration. Our expression reduces to the centripetal acceleration. So because the tangential velocity is related to the angular velocity through the relation Vt equals r omega, an alternative form of centripetal acceleration is shown here. And let's look at the dimensions. So understanding that physical acceleration can occur only if some force is present. For example, if a car travels in a circle on a flat ground, the force of the static friction between the tires and the ground provides the necessary centripetal force. Note that the centripetal acceleration is always directed towards the center of rotation. We have been looking at circular motion and constant speed, but an object moving in a circle, but is speeding up or slowing down, a tangential component of acceleration is also present. Because the tangential and centripetal components of the acceleration are perpendicular to each other, we can find the magnitude of the total acceleration with the Pythagorean theorem as shown. So let's have another question here. So a racetrack is constructed such that two arcs of radius 80 meters at A and 40 meters at B are joined by two stretches of straight tracks as in the figure. In a particular trial run, a driver travels at constant speed of 15 meters per second for one complete lap. In this case, the ratio of the tangential acceleration at A and B is, and the answer is the tangential acceleration is 0 at those points. And the reason is the tangential speed is constant, and thus the tangential acceleration is 0. So in a particular trial run, the driver driving at 50 meters per second for the complete lap, in this case, the ratio of the centripetal acceleration of A to that of B is what? It's 1/2. So the centripetal acceleration A sub c equals v squared over r is inversely proportional to the radius when the tangential speed is constant. And the same question, but we're just asking in this case, the angular speed is greatest where? And the answer is at B. The angular speed omega equals Vt over r is inversely proportional to the radius when the tangential speed is constant. Okay, as an object moves in a circular path with constant speed v, which of the following statements is true concerning the object? Both its velocity and acceleration are changing is the answer. So both the velocity and the acceleration are changing in direction. So neither of these vector quantities is constant. So let's think about this situation. And so a puck is attached to a string of length r, rotating in a horizontal plane of constant speed. We can apply Newton's second law of motion to problems involving circular motion. An object can have a centripetal acceleration only if something external force acts on it. For a ball whirling in a circle at the end of a string, the force is the tension in that string. For a car moving on a flat circular track, the force is friction between the car and the track. A satellite in a circular orbit around the Earth has a centripetal acceleration due to the gravitational force between the satellite and Earth. Beware that some books use the term centripetal force, quote, which can be given the mistaken impression that it is a new force of nature. This is not the case. The adjective centripetal in, quote, centripetal force simply means that the force in question acts towards a center. So let's consider a puck of mass m when it is tied to a string of length r and is being whirled at constant speed in a horizontal circular path as illustrated in the figure. Its weight is supported by a frictionless table. Why does the puck move in a circle? Because of its inertia. The tendency of the puck is to move in a straight line. However, the string prevents motion along a straight line by exerting a radial force on the puck, a tension force that makes it follow the circular path. The tension T is directed along the string towards the center of the circle as shown in the figure. So in general, when converting Newton's second law to polar coordinates, we get an equation relating the net centrifugal force, F sub c, which is the sum of the radial components of forces acting on the given object, to the centripetal acceleration. The magnitude of the net centripetal force equals the mass times the magnitude of the centripetal acceleration as shown in the equation here. A net force which causes a centripetal acceleration acts towards the center of the circular path and affects a change in the direction of the velocity vector. Imagine if that force suddenly vanishes, then the object would immediately leave its circular path and move along a straight line tangential to the circle. Centripetal or center fleeing forces also exist, such as the normal force that prevents an object from falling towards the center of the Earth. So here we have an illustration of small sats, CubeSats, in orbit around the Earth. And so a radial force is a vector and has a circular, has a direction. Newton's law, second law for uniform circular motion, involves forces that are directed either towards the acceleration, towards the center of a circle or away from it. A force acting towards the center of the circle is by convention negative. Examples include the gravity force of a satellite on a string tension, force on a satellite, or a string tension of a whirling yo-yo. Force acting away from the center of the circle is positive. Examples of this include normal forces on a car traveling over the circular crest of a hill, or the force propulsion between electric charges. In a similar way, centripetal acceleration is negative because it acts towards the center of the Earth, of the circle. So Newton's law for uniform circular motion can be written as a vector where the forces V sub r are the radial forces acting on mass m. Positive, the force is away from the center of the circle, and negative, the force is towards the center of the circle. Centripetal or center-seeking forces have negative radial components, whereas centripetal or center-fleeing forces have positive radial components. So here is a problem-solving strategy for forces that cause centripetal acceleration. So as usual, you start with a diagram of the objects under consideration, labeling all forces that act on it. Number two, you choose a coordinate system that has one axis perpendicular to the circular path followed by the object, which is the radial direction, and one axis tangential to the circular path, which is the tangential or angular direction. The normal direction perpendicular to the path of motion is also often needed. Number three, you want to find the net forces F sub c towards the center of the circular path, where the summation of F sub r is the sum of the radial components of the forces. This net radial force causes the centripetal acceleration. Number four, you want to use Newton's second law for radial, tangential, and normal directions as required. Remember that the magnitude of the centripetal acceleration for the uniform circular motion can always be written as shown. And finally, you want to solve for the unknown quantities. So in this figure, we have a quote, fun-loving student loses her grip and falls across a tangential line to the rim of the merry-go-round. So maybe this might have happened to you when you were a kid. Anyone who has ridden a merry-go-round has experienced what feels like a center fleeing force. Holding on to the rail and moving towards the center feels like walking on a steep hill. After the so-called centrifugal force is fictitious. In reality, if you are riding the merry-go-round, you are exerting a centripetal force on your body, with your hands and arm muscles. Also, a smaller centripetal force is exerted by the static friction between your feet and the platform. If you grip slips, you won't be flung radially away. You would go off at a straight line tangential to the point in space where you let go of the railing, as you're seeing in the picture. You would land at a point that is farther away from the center, but not by fleeing the center, although along a radial line. Instead, you would travel perpendicular to the radial line, traversing an angular displacement while increasing your radial displacement, as you can see in the figure. So here's a picture of the Earth and the moon from an observer point of view. And so before 1686, lots of data had been collected on the motions of the moon and planets, but no one had a clear understanding of the forces affecting them. In that year, Sir Isaac Newton provided the key that unlocked the secrets to the heavens. He knew that a net force had to be acting on the moon. If it were not, the moon would move in a straight line path rather than in its almost circular orbit around Earth. Newton reasoned that it was the same kind of force that attracted objects such as apples close to the surface of the Earth, when he called it the force of gravity. In 1687, Newton published his works on the law of universal gravitation. Important find, and here we get a chance to be looking that through a little bit more. So in the figure that we have the gravitational forces between two particles is attractive and acts along the line joining the particles. Note that according to Newton's third law, F12 is equal to minus F21. If two particles with mass M1 and M2 are separated by a distance r, a gravitational force F acts along a line joining them with magnitude given by the equation shown. When G is a constant of proportionality called the constant of universal gravitation, the gravitational force is always attractive. This force law is an example of the inverse square law in that it varies as 1 over the square of the distance between particles. From Newton's third law, we know that the force exerted by M1 and M2, designated F12, is the figure. In the figure is the equation in magnitude, but opposite in the direction to the force F21 exerted by M2 on M1, forming an action-reaction pair. Another important fact is that the gravitational force exerted by the uniform sphere on a particle outside the sphere is the same as the force exerted in the entire mass of the sphere we're concentrated on at its center. This is called Gauss's law, where the German mathematician and astronomer Gauss, and is also true of electric fields, which we will encounter in topic 15. Gauss's law is a mathematical result true because the forces fall off as the inverse square of the separation between the particles. So here, near the surface of the Earth, the expression F equals mg is valid, but you should be aware that the free fall acceleration g varies considerably with altitude above the Earth, as you can see is a table. And so here we're getting a chance to see how this the acceleration of gravity changes with height. And so thus, if you're in the space station, you're not going to have nearly as much gravity. And so that's where for the most part, it feels like they're not constrained by gravity at all. It is a fairly minor component, relatively speaking, at that height. So let's consider this question. So a ball is falling towards the ground. Which of the following statements are false? And the answer to this is statements B and C are false. According to Newton's law of universal gravitation, the force between the ball and the Earth depends on the product of their masses, as both forces, that of the ball and of the Earth, and that of the Earth and the ball, are equal in magnitude. This follows also, of course, from Newton's third law. The ball has large motion compared to the Earth because, according to Newton's second law, the force gives a much greater acceleration to the small mass of the ball. Here's another question. So a planet that has two identical moons with identical mass, M1 is in a circular orbit of radius r. Moon 2 is in a circular orbit of 2r. The magnitude of the gravitational force exerted on the planet of Moon 2 is 1/4 as large as the gravitational force on the planet at Moon 1. And that's it because the force from gravity is F equals G M, capital M, small m divided by r squared. The gravitational force is inversely proportional to the square of the radius of the orbit. So that's the reason why it's 1/4. Okay, well, let's talk about the measurement of the gravitational constant. So in the figure, we have a schematic diagram of the Cavendish apparatus for measuring G. The smaller spheres of mass M are attracted to the larger spheres of mass capital M, and the rod rotates through a small angular angle. A light beam reflected from the mirror on the rotating apparatus measures the angle of rotation. You might be wondering where the gravitational constant G came from. It came from, it was first measured in an important experiment by Henry Cavendish in 1798. His apparatus is shown in the figure and consists of two small spheres, each of mass m, fixed to the end of a light horizontal rod suspended by a thin metal wire. Two large spheres, each of mass m, were placed near the smaller spheres. The attractive force between the smaller and larger spheres caused the rods to rotate in a horizontal plane and the wire to twist. The angle through which the suspended rod rotated was measured with a light beam reflected from a mirror attached to the vertical suspension. This experiment was carefully repeated with different masses at different separations. In addition to providing a value for G, the results show that the force is attractive, proportional to the product of the two masses, and inversely proportional to the square of the distance r. So in this figure, we have a mass M is moving radially away from the Earth. The potential energy of the Earth mass system, which is given in the equation there at the Earth's surface, increases towards a limit of zero as the mass M travels away from the Earth, as shown on the graph. You may remember the potential energy associated with an object can be calculated from the equation PE equals to mgh, where h is the height of the object above or below some reference level. This equation is valid only when the object is near the Earth's surface. For an object high above Earth's surface, such as a satellite, an alternative must be used because G varies with the distance from the surface, as we saw in the table on the previous slide. The gravitational potential energy associated with an object of mass M at a distance r from the center of the Earth is given in the equation shown, where ME is the mass of the Earth and r is greater than or equal to RE, the radius of the Earth. As before, gravitational potential energy is as a property of a system, in this case, the object of mass M and the Earth. The figure illustrates this equation. This equation is valid for the special case where the zero level for potential energy is at an infinite distance from the center of the Earth. Recall that the gravitational potential energy associated with an object is nothing more than the negative of the work done by the force of gravity in moving the object. If an object falls under the force of gravity from a great distance, which is effectively infinity, this change in gravitational potential energy is negative, which corresponds to a positive amount of gravitational work done on the system. This positive work is equal to the change in kinetic energy, which is also positive. So in this figure, relating the general form of the gravitational potential energy to mgh is what we're trying to consider. The height h is greatly exaggerated for clarity. when you look at the equations for gravitational potential energy, you may be wondering what happens to mgh. The expression is still valid when h is small compared to the Earth's radius. To see this, let's write the change in potential energy as an object is raised from the ground to height h, using the general form for gravitational potential energy, as illustrated in the figure. After finding a common denominator and applying some algebra, which you can do on your own, we obtain this expression. When the height h is very small compared with RE, h can be dropped from the second factor in the denominator. Substituting this into the first expression, we get the result as shown. As you may recall, the free fall acceleration at the surface of the Earth is given by the equation here. So for R equals to RE, we get mgh. And that's an approximate relationship. So if an object is projected upward from Earth's surface with a large enough speed, it can soar off into space and never return. The speed is called the Earth's escape speed. It is also commonly called the escape velocity, but in fact, it is more properly, you could consider it a speed. The Earth's escape speed can be found by applying conservation of energy. Suppose an object's mass m is projected vertically above the Earth's surface with an initial speed v sub I. The initial mechanical energy, kinetic plus potential energy of the object's Earth system is given by the equation shown. We neglect air resistance and assume the initial speed is just large enough to allow the object to reach infinity with speed of 0. This value of v sub I is the escape speed, E sub escape, ESC, where the object is at an infinite distance from Earth, is kinetic, its kinetic energy is 0 because v sub f is 0. And the gravitational potential energy is also 0 because 1 over r goes to 0 as r goes to infinity. That means that the total mechanical energy is 0. And the law of conservation of energy gives this equation. Solving, we get the escape speed that's just shown on the bottom. And so that's the amount of energy that's required to propel a satellite or astronauts out of the Earth's gravitational force and out into space beyond Earth. So here we're listing the escape speeds for various planets, the moon and the sun in this table. And the escape speed and temperature determine to a large extent whether a world has an atmosphere. And it's also what the constituents of the atmosphere are. Planets with low escape speed, such as Mercury, generally don't have much atmospheres because the average speed of gas molecules is close to the escape speed. Venus has a very thick atmosphere, but it's almost entirely carbon dioxide, a heavy gas. The atmosphere of the Earth has very little hydrogen or helium, but has retained the much heavier nitrogen and oxygen molecules. So this might be interesting just to give you an idea of these relative escape velocities. And Pluto, you may have heard, was demoted to no longer being a planet. You can see that its escape speed or velocity is even lower than that of the moon, in giving you a perspective of that. And of course, for the larger planets, these numbers would be a lot larger. So Jupiter and Saturn, the largest planets in our solar system, they're going to be a lot bigger. So as we discussed back in topic 2 in early history, people generally regarded the Earth as the center of the universe. And this was the geocentric model was developed by the Greek astronomer Ptolemy in the 2nd century AD, and was accepted for nearly 1400 years. In 1543, the Polish astronomer Nicholas Copernicus showed the Earth and the other planets revolving circular orbits around the sun, called the heliocentric model. Danish astronomer Tycho Brahe made accurate astronomical measurements over a period of 20 years, providing the data for the currently accepted model of the system. Brahe's precise observations of the planets and 777 stars were carried out with nothing more elaborate than a large sextant and a compass, because the telescope hadn't been invented yet. Then it was German astronomer Johannes Kepler, who was Brahe's assistant, acquired Brahe's astronomical data and spent 16 years trying to deduce a mathematical model for the motions of the planets. After many laborious calculations, he found that Brahe's precise data on the motions of Mars about the sun provided the answer. Kepler's analysis showed that the concept of circular orbits around the sun had to be abandoned. He eventually discovered the orbits of Mars could be accurately described by an ellipse. So that's what we're showing here in this picture, is that there weren't circles, there were ellipses. And so if you describe the orbits as ellipses around the sun, one foci, and he would generalize that this analysis to include the motions of all planets. So his analysis is summarized in 3 statements known as Kepler's laws, and there's various levels of sophistication that you can be using to play this out. So number 1, all planets move in elliptical orbits with the sun at one of the focal points. So that's number 1. Number 2, a line drawn from the sun to any planet sweeping out equal area and equal time intervals. That's number 2. And number 3, the square of the orbit periods of any planet is proportional to the cube of the average distance from the planets to the sun. Wow, that's a whole lot, and just some fairly dense question statements there. So here we'll look at Kepler's first law. So in the figure above, we have the sum P plus Q is the same for every point on the ellipse. And for V, if the solar system, the sun is at one focus of the elliptic orbit of each planet, and the other focus is empty. The first law arises as a natural consequence of the inverse square nature of Newton's law of gravitation. Any object bound to another by a force that varies with 1/r squared will move in an elliptical orbit. As shown in the top figure, an ellipse is a curve drawn so that the sum of the distances from any point on the curve to the 2 points called focal points or foci, singular focus is always the same. The semi-major axis, A, is half the distance of the line that goes across the ellipse and contains both foci. For the sun-planet configuration shown in the bottom figure, the sun is one of the focus, and the other focus is empty. Because the orbit is an ellipse, the distance from the sun to the planet is continually changing. And just to keep in mind that these the foci shown are exaggerated. You don't have ellipses that are that skewed, but just for giving a good illustration, that is probably helpful for you to be seeing it that way. Here we have Newton's second law. And so the 2 areas swept out by the planets in the elliptical orbit above the sun are equal if the time interval between point A and B is equal to the time interval between C and D. And so it almost would be better if I had an illustration to show this. And if I have time, I can do that offline. Kepler's second law states that a line drawn from the sun to any planet sweeps out the equal area in equal time intervals. So if you were looking at here, it would actually be so these areas are always going to be the same. And so what you can see is, since this is a longer arc, it actually goes faster here going from C to D than it goes from A to B. And that's one of the ways that you can get that this takes place in the same amount of time. So if you consider a planet in an elliptic orbit about the sun, as shown in the figure, in a given period delta t, the planet moves from point A to B. Planets move more slowly at the side of the orbit because it's farther away from the sun. On the opposite side of the orbit, the planet moves from point C to D at the same amount of time delta t, moving faster because it's closer to the sun. Kepler's second law states that any 2 wedges formed as in the figure, are always have the same area. As will be seen in topic 8, Kepler's second law is related to physical principles known as the conservation of angular momentum. Now for Kepler's third law, we can derive Kepler's third law for a special case of a circular orbit. So consider a planet of mass m sub p moving around the sun, which has a mass of m sub s in a circular orbit. Because the orbit is circular, the planet moves as a constant speed v. Newton's second law, his law of gravitation and centripetal acceleration, then gives the equation shown. The speed v of the planet in the orbit is equal to the circumference of the orbit divided by the time required for one revolution, t, called the period of the planet. Here we are substituting our expression and simplifying, solving for t squared. We get Kepler's third law for motion, where k sub s is a constant. So this equation is Kepler's third law for circular orbits. The orbits of most of the planets are very nearly circular. Comets and asteroids, on the other hand, usually have highly elliptical orbits. For these orbits, the radius r must be replaced with a, the semi-major axis, half the longest distance across the elliptical orbit. This is also the average distance of the comet or asteroid from the sun. A more detailed calculation shows that k sub s actually depends on the sum of both the masses given in the planet and the sun's mass. The masses of the planets, however, are negligible compared with the sun's mass, and so often can be neglected, meaning the equation is valid for any planet in the sun's family. If we consider the orbit of a satellite much as the moon around the Earth, then the constant has a different value, with the mass of the sun replaced by the mass of the Earth. So when time is measured in Earth years and the semi-major axis in astronomical units, where 1 AU is the distance from the Earth to the sun, Kepler's law takes the simple form shown. This equation can be easily checked. Earth has a semi-major axis of 1 astronomical unit by definition. It takes 1 year to circle the orbit. This equation, of course, is valid only for the sun and the planets, asteroids, and comets. The table shows some useful planetary data. The very last column shows the t squared divided by r3 and is very nearly constant. So have a look at that, and that may be some useful data to refer to later. So we have a couple of questions here. Let me just check and see how many we got. So we'll kind of go quickly through these, and then we'll continue on from that. So suppose an asteroid has a semi-major axis of 4u. How long does it take the asteroids to go around the sun? The answer is 8 years. Estimate the speed of the Earth relative to the sun in meters per second. It's between 3,000 and 30,000. Estimate the acceleration of the Earth relative to the sun in meters per second, and the answer is between 0.003 and 0.03. If an object is at rest on the equator, estimate its speed relative to the center of the Earth in meters per second, and the answer is between 100 and 1,000. An object is at rest on the equator, estimate its acceleration relative to the center of the Earth in meters per second, and the answer is between 0.01 and 0.1. Estimate the speed of the moon relative to the center of the Earth in meters per second. The answer is between 300 and 3,000. Estimate the acceleration of the moon relative to the center of the Earth in meters per second squared, and the answer is less than 0.003. A small ball is released from the rest at position A and rolls down the vertical circular track under the influence of gravity. When the ball reaches position B, which of the indicated directions most nearly corresponds to the direction of normal force of the ball? And the answer is number 1. So a small ball is released from rest at position A and rolls down the vertical circular track under the influence of gravity. When the ball reaches position B, which of the indicated direction most nearly corresponds to the direction of the ball's acceleration? And the answer is number 2. And so what about which of the indicate the direction most nearly corresponds to the direction of the net force of the ball? And the answer is number 2. And in this one, a mass of 5 kilograms is released from rest on a smooth incline, making an angle of 37 degrees to the horizontal. The tangential component of the acceleration is closest to, and the answer is 6 meters per second squared. So here have something similar. A mass of 5 kilograms is released from rest on a smooth incline, making an angle of 37 degrees to the horizontal. The radial component of acceleration is closest to 0 meters per second. A ball is rolled on it up an incline so that it goes part way up and then rolls back down. Which of the graph below could represent its tangential component of acceleration versus time from the instant it was released until it returns to the starting point? The answer is number 2. An iceberg weighing 1,000 tons is floating in the North Atlantic. Consider the gravitational forces on the iceberg due to the Earth, the Moon, and the Sun. Put these gravitational forces in order of increasing magnitude. You do not need to do any calculation. Using reasoning or simply guessing is just fine. So the answer is the Moon, which would be less than the Sun, which would be less than the Earth. 2 identical objects are released from rest from heights r and 2r above the surface of the Earth after traveling a distance r/2. Which object has a larger speed? And the answer is object number 1. So after traveling a distance r2, which object has a larger energy? And the answer is B. So a planet has the orbit shown below. Using the 8 labeled points to answer the question, where is a planet when the total energy of the system is the largest? And the answer is the total energy is the same everywhere. So at which points is the speed of the planet the smallest? The answer is 1 and 5. At what points is the y component of the velocity the largest? And the answer is number 1. At what point is the x-axis of the velocity largest? And the answer is number 3 and number 7. Okay, that's a lot of information that we've covered. We'll just finish up with a few slides with a summary here. And so for angular velocity and angular acceleration, the average angular velocity of a rigid object is defined as a ratio of the angular displacement to the time interval delta t, where omega AV is in radians per second. The average angular acceleration of a rotating object is defined as a ratio of the change in angular velocity to the time interval delta t, where alpha AV is in radians per second squared, radians per second, radians per second squared. Rotational motion under constant angular acceleration, if an object undergoes rotational motion about a fixed axis under a constant angular acceleration, its motion can be described with a set of equations shown. Problems are solved as in one-dimensional kinematics. For tangential velocity, tangential acceleration, and centripetal acceleration, when an object rotates about a fixed axis, the angular velocity and angular acceleration are related to the tangential velocity and the tangential acceleration through the relationship shown. Any object moving in a circular path must have a net force exerted on it that is directed towards the center of the path. Some examples of forces that cause centripetal acceleration are the forces of gravity, such as the motion of a satellite and the forces of tension in a string. For Newton's gravitation, Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely directed to the square of the distance r between them. G is a constant of universal gravitation. For gravitational potential energy, a general expression for gravitational potential energy is shown. This expression reduces to PE equals mgh, close to the surface of the Earth, and holds for other worlds through replacement of the mass me. Problems such as finding the escape velocity from Earth can be solved by using this equation in the conservation of energy equation. So Kepler's law of planetary motion, so we have 3 of them. Kepler derived the following 3 laws of planetary motion. Number 1, all planets move in elliptical orbits with the sun at one of the focal points. Number 2, a line drawn from the sun to any planet sweep out equal areas in equal time. And number 3, the square of the orbital period of the planets is proportional to the cube of the average distance from the planets to the sun. The third law can be applied to any large bodies and its system of satellites by replacing the sun's mass with the body's mass. In particular, it can be used to determine the mass of the center body once the average distance to a satellite and its period are known. Okay, well, thank you very much. And that will be it for this lecture.